Assalamualaikum and good day. This video will explain a special type of linear programming problem, which is the transportation problem. This problem can be solved by the simplex algorithm, but specialized algorithm for the problem is much more efficient. Let's begin with a brief description of transportation problem. The transportation problem involves a set of m supply points from which a good is shipped. Supply point I can supply SI unit. Let's draw a graphical representation of this point. We have m supply points I equals to 1, I equals to 2, until the m supply point, I equals to m. And every supply points can supply SI unit. For example, the first supply point can supply S1 units of goods. Supply point 2 can supply S2 units of goods. And the M supply point can supply SM units of goods. Okay, next, we have a set of N demand points to which the good is shipped. This demand point must receive DJ units of the shipped good. Okay, in this case, we have N demand points. Okay, we have J equals to 1, J equals to 2, until the N demand point. Okay, where J equals to N. And every demand point needs to receive a number of goods. Okay, so the first demand point should receive DJ unit of good, D1 unit of good. The second demand points must receive D2 units of goods. And for the N demand point, this point must receive Dn unit of goods. And each unit produced at supply point I and shipped to the demand point J incurs a variable cost of Cij. Means every supply point needs to deliver goods to each demand point. Okay. So from the first supply point to the first demand point, also this point will deliver good to second demand point, to the next demand point, and it also should deliver goods to the N demand point. The second supply point also need to deliver good to the first demand point, to the second demand point, to the J demand point, and also to the end demand point. The same process also applied to the M supply point. The M supply point supply goods to the first demand point, to the second demand point, to the jth demand point, and to the end demand point. And this process involves cost. In this figure, we can see that the cost to deliver goods from supply point 1 to the first demand point is C11, where C represents cost. C12 is the cost to deliver goods from first supply point to the second demand point. And cost to ship goods from the first supply point to the end demand point is C1N. C21 is the cost to deliver goods from second supply point to the first demand point. Okay, so we can write the cost from every supply point to the demand point. So C22 is the cost from second supply point to the second demand point, and C2N is the cost to deliver goods from second supply point to the end demand point. For the M supply point, the cost involved is CM1, CM2, CMJ, and CMN. So this is the process of transporting goods from supply point to demand point. The general model of the transportation problem is shown here, where Xij represent the decision variable and the value of each variable show the number of units shipped from supply point I to demand point J. The number of decision variable in a transportation problem is M times N. From this figure, the variable involved in the transportation problem is X11, X12, X13 until X1N. Also, X21, X22, X until X2N, and XM1, XM2 until the last variable is XMN. Okay, we know that the number of variables in a transportation problem is M times N. For example, a problem has 2 supply points and 3 demand points. Okay, we know that the number of supply point is 2. Therefore, m equals to 2 and 3 demand points. So, n equals to 3. Therefore, this example has 6 decision variables. The variables are x11, x12, x13, x21, x22, and x23. The objective of the problem is to minimize the cost. So from the formula, we can see that we need to multiply the cost by the variable and then sum them up. Okay, for this example, the objective function will be minimize z equals to summation of I equals to 1 until 2, summation j equals to 1 until 3, Cij xij. Therefore, z equals to, we start with I equals to 1 and j equals to 1. So we have C11, X11. Okay, we complete the inner summation. Okay, so now j becomes 2. So plus C12, X12. Now j increase to 3. So plus C13, X13. We already complete for j. Now we go back to the outer summation. So now I equals to 2. So plus C21, X21 plus C22, X22 plus C23, X23. So, this is the objective function of this example. Next, write the constraint. There are two types of constraint in the transportation problem. The first type is the supply constraint. And the other is the demand constraint. Using this example, okay, the constraint of the first supply point is where I equals to 1 is x11 plus x12 plus x13 equals to S1. Okay, because we want to find the constraint for the first supply point. Okay, the capacity of the first supply point is S1. So, from the first supply point, this constraint This constraint represents a shipment of goods from supply point 1. Constraint for the second supply point is X21 plus X22 plus X23 equals to S2. Only two supply constraints since this example has two supply points. For the demand constraint, the constraint of the first demand point where J equals to 1 is X11 plus X21 equals D1. And the second demand points constraint is X12 plus X22 equals to D2. And the last constraint is X13 plus X23 equal to D3. The number of constraints is given by M plus N. So we have 5 constraints. And lastly, write the sign restriction. Xij greater than or equal to 0. Okay, for this one, we have Xij greater than or equals to 0, where I equals to 1, 2, and J equals to 1, 2, and 3. It is desirable to formulate a balanced transportation problem. The problem is said to be a balanced transportation problem if the total supply units equal to total demand units. Otherwise, the problem is said to be unbalanced. For that case, a dummy supply or a dummy demand must be added to balance the problem. The cost for the dummy variable must be equal to 0. Now, let's continue our discussion for transportation problem by formulating a linear programming model of the following situation. Tenaga Malaysia Berhad (TMB) has 3 electric power plants that supply the needs of 4 cities: Rawang, Rasa, Kuala Kubu Baru, and Bukit Beruntung. Each power plant can supply the following numbers of kilowatt hours of electricity. Plant 1 can produce 3,500 kilowatt hour of electricity. Plant 2 produce 5,000 kilowatt hour of electricity. Plant 3 can supply 4,000 kilowatt hour. The peak power demands in these cities which occur at the same time are as follows. Rawang demand 4,500 kilowatt hour of electricity. Rasa must receive 2,000 kilowatt hour of electricity. KKB and Bukit Beruntung demand 3,000 kilowatt hour of electricity respectively. The cost of sending 1 kilowatt hour of electricity from plant to city depends on the distance of electricity must travel and is given in Tableau 5.1. Formulate an LP model to minimize the cost of meeting each city's peak power demand. This table summarizes the problem. Okay, we have 3 supply points. Let's label the supply point. This is I equals to 1, I equals to 2, and I equals to 3. For the demand point, we have J equals to 1, J equals to 2, this is J equals to 3, and J equals to 4. This is the cost to deliver 1 kilowatt hour of electricity from plant 1 to Rawang. And 6 cents is the cost to deliver 1 kilowatt hour of electricity from plant 1 to Rasa. This is supply unit from plant 1. 5,000 is the supply unit from plant 2. This is S3. And demand from Rawang is 4,500. So this is D1. D2, 2,000 is the demand from Rasa. This is D3 and D4. Before we formulate the model, let's check whether the problem is balanced or unbalanced. The total supply unit is 3,500 plus 5,000 plus 4,000. We add these supply units, we get 12,500. And the total of demand units is 4,500 plus 2,000 plus 3,000 plus 3,000. So we get 12,500. Since the total supply and total demand are equal, the TMB problem is a balanced transportation problem. There are 12 variables involved in this problem since it has 3 supply points and 4 demand points. M equals to 3 and N equals to 4. Xij represent the number of electricity in kilowatt hour produced at plant I and sent to city J, where I is equal to 1, 2, and 3, and J is equal to 1, 2, 3, and 4. In terms of these variables, the total cost of supplying the power demands to the cities may be written as, to minimize the cost, Z equals to 8x11 plus 6x12 plus 10x13 plus 9x14. Okay, we multiply the cost, the shipping cost, with the variable. This is the cost of shipping power from plant 1. Next, we go to plant 2. We have 9x21 plus 12x22 plus 13x23 plus 7x24. This cost comes from plant 2. And for plant 3, we have 14x31 plus 9x32 plus 16x33 plus 5x34. So this is the objective function of the problem. TMP faced two types of constraints. First, the total power supplied by each plant should be equal to the plant's capacity. For example, the total amount of power from plant 1 to the 4 cities must equal to 3,500 kilowatt. Therefore, the constraint can be expressed as x11 plus x12 plus x13 plus x14 equals to 3,500. This is the constraint of plant 1. In a similar fashion, we can find constraints that reflect plant 2's and plant 3's capacities. So, the second constraint is x21 plus x22 plus x23 plus x24 equal to 5,000. And constraint for plant 3 is x31 plus x32 plus x33 plus x34 equal to 4,000. Next, we need constraints that ensure that each city will receive sufficient power to meet its peak demand. For example, Rawang must receive 4,500 kilowatt-hour power. So, we obtain the following constraint. x11 plus x21 plus x31 equal to 4,500. Similarly, we obtain a constraint for other cities. A constraint that ensures that a location receives its demand is a demand constraint. Okay, constraint for Rasa is x12 plus x22 plus x32 equal to 2,000. Next, Kuala Kubu Baru demand constraint is x13 plus x23 plus x33 is equal to 3,000. And the last constraint is x14 plus x24 plus x34 equals to 3,000. Lastly, we need to add a sign restriction. All variables are non-negative. Transportation problem is specified by the supply, the demand, and the shipping cost. so the relevant data can be summarized in a transportation tableau. The cell in row I and column J of a transportation tableau correspond to the variable xij. For example, the first cell belongs to variable x11. The second cell is for variable x12. This is cell for x13, x14. And the last cell is x34. And we write the shipping cost of the corresponding variable in the small square. We write 8 cents here in this small square. This is the cost to ship 1 kilowatt hour of electricity from plant 1 to Rawang. In this square, we write 6. Okay, we need to complete all small squares. Write the cost for every variable. We also need to write the supply units and demand units for every point. The supply unit from plant 1 is 3,500. 5,000 is the supply unit from plant 2 and 4,000 from plant 3. And these are the demand units. Next, we need to find a basic feasible solution or initial basic variable to solve the problem. One of the methods that can be used to find a basic feasible solution for a balanced problem is the northwest corner method. To find a basic feasible solution by the northwest corner method, we begin in the upper left corner of the transportation tableau and set the variable x11 as large as possible. Clearly, x11 can be no larger than the smaller of S1 and D1. In the TMB tableau, we set x11 equal to minimum between S1 and D1. So minimum S1 is 3,500 and D1 is 4,500. Between these two numbers, 3,500 is the smaller. Therefore, x11 is equal to 3,500. We cross out row 1. And change D1 to 4,500 minus 3,500. So the formula is D1 minus S1. So 4,500 minus 3,500. So we get the new D1 is 1,000. Next, the most northwest remaining variable is x21. So we set x21 as minimum between S2 and D1. So minimum S2 is 5,000 and D1 is 1,000. So from here we compare 5,000 and 1,000. 1,000 is smaller than 5,000. Therefore, X21 is 1,000. Since X21 equal to D1, therefore, we need to cross out column 1. And then reduce the value of S2 by 1,000. So 5,000 minus 1,000 is equal to 4,000. Continue applying this procedure to the most northwest cell in the tableau that does not lie in a cross-out row or column. The most northwest available variable is now X22, and the value is minimum S2 D2. So we compare 4,000 and 2,000. So we can set the value of X22 is 2,000. We choose the smaller number. Okay, and since X22 equals to D2, therefore we cross out the second column of D2. And then reduce the value of S2. Okay, so now S2 is equal to 4,000 minus 2,000 is 2,000. Among this cell, X23 is the most upper left corner. Therefore, X23 is minimum S2 D3 equal to minimum S2 is now 2,000 and D3 is 3,000. Therefore, X23 is 2,000. We cross out row 2 and reduce D3 by 2,000. So we get 3,000 minus 2,000. D3 now is 1,000. Next, we choose X33. X33 is equal to minimum S3 D3 equals to minimum between 4,000 and 1,000. Therefore, X33 is 1,000. We cross out column 3 and reduce S3 by 1,000. Now S3 is 4000 minus 1000 becomes 3000. Eventually, we come to a point where there is only one cell that can be assigned a value. Assign this cell a value equal to S3 or D4 and cross out both row and column. Now a basic feasible solution has been obtained. The basic variables are x11, x21, x22, x23, x33 and x34. The number of basic variables can be determined from this formula. M plus N minus 1. Okay, in the MB problem, the number of variables is 3 plus 4 minus 1 is equal to 6. Okay, so here we have 6 basic variables. 1, 2, 3, 4, 5, and this one is 6. The other method that can be used to find the starting basic feasible solution, BFS, or the initial basic variable is the minimum cost method. The steps in this method is similar to the steps in the northwest corner method. The difference is how to choose the cell. We choose the cell with the smallest shipping cost. We label the variable xij as the value of either si or dj. We choose the smaller value among these two variables. And then we cross out either row I or column j and then reduce the supply or demand of the non-crossed out row or column by xij. And then we choose from the cell that do not lie in a crossed out column or row and repeat the procedure. Let's discuss example 5.4. In this problem, we have M equals to 1, 2, 3, 3 supply points, and N equals to 1, 2, 3, 4, 4 demand points. Therefore, we have the number of basic variable is 3 plus 4 minus 1 equals to 6. Okay, so we need to find the BFS of this problem by using the minimum cost method. Okay, we start with the cell with the smallest cost. Okay, here x22 has the smallest cost. Therefore, the value of x22 is the minimum between 10 and 8. Okay, the value of x22 is 8. Okay, we write the number 8 here and then we cross out the column, the second column, And then reduce the value of S2 by 8. Then we get 2 here. Next, we move to the other cell that has smallest cost. Okay, since we have two cells with cost 2, and that we can choose either one. Here I choose cell X11. Okay, the value of X11 is minimum between 5 and 12. Therefore, the value of this cell is, the value of X11 is 5. Okay, we write 5 here. And since 5 comes from S1, therefore, we cross out the first row and reduce D1 to 7. 12 minus 5. Next, we move to cell X21. X21 is minimum 2 and 7. Okay, is equals to 2. Okay, the value of this variable is 2. And we cross out the second row. And D1 becomes 5. Next, we still have 3 cells. Among these 3 cells, X31 has the smallest cost. Okay, the value of this variable is minimum 15 and 5. The value is 5. Alright, then we cross out the first column and reduce D3 from 15 to 10. 15 minus 5 is 10. Next, we move to cell 33. X33 is minimum 10 and 4. And the value of this variable is 4. Write 4 here. And cross out column 3. And S3 now is 6. Okay, for the last cell, make sure the value of SI and DJ is equal. Here S3 is 6 and D is 6. Okay, means we have a balanced transportation problem. And the value of this cell is 6. And we cross out either column or row. Okay, we have 1, 2, 3, 4, 5, 6 basic variables. And the value of other variables is 0. Okay, means these variables are NBV. Okay, to calculate the value of Z, okay, we multiply the value of Xij and its cost. Okay, we know our objective function is Z equals to summation of I from 1 until M and J from 1 until N Xij times Cij. Okay, so from here we know the value of X11 is 5 times its cost is 2 plus, okay, 0, we ignore the NBV, Okay, then we have next x21 is 2 and the cost is 2 plus 8 times 1 plus 5 times 3 plus 4 times 4 and 6 times 6. We get z equals to 89. This is the value of initial z. That's all for now. Thank you.